In our daily lives, we often take bridges for granted. These marvels of engineering quietly support our commutes, connect communities, and facilitate the flow of commerce. However, beneath their sturdy facades lies a growing concern: the impact of climate change on bridge infrastructure. As we navigate an era of unprecedented environmental shifts, the very structures we depend on face challenges that their designers never anticipated. The aging bridge crisis. The United States, like many developed nations, is grappling with an aging bridge infrastructure. The average bridge in the U.S. is approximately 45 years old, a testament to the durability of these structures, but also a cause for concern. When these bridges were constructed, engineers designed them according to the standards and environmental conditions of their time. Unfortunately, these designs did not account for the dramatic climate changes we are now experiencing. What's particularly alarming is that even today, bridge design standards do not adequately factor in climate change. Current guidelines rely on climate data from the past 200 years, a historical perspective that fails to capture the rapidly evolving environmental challenges of our time. This oversight leaves our bridges vulnerable to a host of climate-related threats that could compromise their integrity and safety. Thermal stress, a growing concern. One of the primary challenges facing bridges in a warming world is thermal stress. As temperatures rise, materials expand, potentially causing critical components to misalign or fail. Traditional bridge designs incorporated expansion joints to accommodate these temperature-induced changes. These joints, essentially gaps in the bridge structure, allow for expansion and contraction as temperatures fluctuate. However, expansion joints are not without their problems. They can become clogged with debris such as leaves and dirt, rendering them ineffective. When an expansion joint fails to function properly, it can no longer accommodate the thermal expansion of the bridge materials, leading to structural damage or failure. The situation is becoming increasingly dire as global temperatures continue to rise. Research suggests that depending on the effectiveness of our climate change mitigation efforts, between 60% and 95% of bridges with expansion joints could fail by the year 2100 due to thermal stress alone. This startling projection underscores the urgent need for adaptive strategies in bridge design and maintenance. Modern solutions to thermal stress. Fortunately, engineers have developed more resilient bridge designs to address the limitations of traditional expansion joints. One such innovation is the integral abutment bridge. These structures use elastic connections between bridge components instead of rigid expansion joints, allowing them to better dissipate thermal stress. This design approach not only mitigates the risks associated with thermal expansion, but also eliminates the maintenance challenges posed by debris-clogged expansion joints. Scour, the underwater threat. While integral abutment bridges offer a solution to thermal stress, they face another climate-related challenge: scour. Scour occurs when water flow creates eddies around submerged parts of a bridge, gradually eroding the foundation material. As climate change intensifies rainfall and flooding events, the risk of scour increases dramatically. Current bridge design guidelines base their scour predictions on historical data, which no longer accurately reflect the intensity and frequency of modern weather events. As a result, many bridges are ill-equipped to withstand the increased water flow and flooding brought on by climate change. To combat this growing threat, engineers have developed several innovative solutions. One approach involves installing collars around bridge piers to disrupt the eddies that cause scour. Another method employs sacrificial piles, smaller concrete or metal columns placed upstream of the main structure, to break up water flow before it reaches the bridge foundations. These adaptations can significantly enhance a bridge's resilience to scour, even in the face of more extreme weather events. The silent threat: carbonation and corrosion. Beyond the visible impacts of rising temperatures and increased flooding, climate change poses a less obvious but equally serious threat to bridge infrastructure: accelerated corrosion due to carbonation. This process particularly affects reinforced concrete bridges, which rely on steel rebar for structural integrity. Under normal conditions, the high pH environment within concrete forms a protective layer of iron oxide around steel rebar, preventing corrosion for tens of thousands of years. However, as atmospheric carbon dioxide levels rise, CO2 can penetrate concrete through a process called carbonation. This gradually lowers the pH of the concrete, compromising the protective iron oxide layer and dramatically accelerating the corrosion of steel rebar. The implications of this process are staggering. Without intervention, carbonation could reduce the lifespan of steel rebar from 60,000 years to just 60 years, a thousandfold decrease. This accelerated deterioration poses a significant threat to the long-term stability and safety of concrete bridges worldwide. Combating carbonation and corrosion, engineers and materials scientists are actively developing strategies to mitigate the effects of carbonation on bridge infrastructure. One straightforward approach is to increase the thickness of concrete cover around steel rebar, creating a more substantial barrier against CO2 penetration. Additionally, the application of epoxy or acrylic sealers can help fill microscopic pores in the concrete, further impeding the ingress of carbon dioxide. These solutions offer promise for new construction projects and can be incorporated into renovation efforts for existing bridges. However, their effectiveness ultimately depends on widespread adoption and implementation. The policy challenge. While technical solutions to climate-related bridge vulnerabilities exist, a significant hurdle remains: the slow pace of policy adaptation. Despite the scientific consensus on climate change dating back to the 1970s, bridge construction standards in many regions still do not adequately account for these evolving environmental challenges. This lag in policy implementation can be attributed, in part, to decades of lobbying efforts by fossil fuel industries, which have historically downplayed the urgency of climate change. As a result, many bridges continue to be built and maintained according to outdated standards that do not reflect current climate realities. The path forward. Encouragingly, some nations are beginning to update their bridge construction standards to incorporate climate resilience. These forward-thinking policies represent a crucial step towards safeguarding our infrastructure against the impacts of climate change. However, more widespread action is needed to ensure the long-term safety and stability of bridges worldwide. To effectively address the challenges posed by climate change to bridge infrastructure, a multifaceted approach is required. Updated design standards. Regulatory bodies must revise bridge design and construction standards to reflect current climate projections and incorporate resilience measures. Retrofit programs. Governments should invest in comprehensive programs to assess and upgrade existing bridges, prioritizing those most vulnerable to climate-related risks. Innovation in materials. Continued research and development of climate-resistant materials and construction techniques can enhance the resilience of new and existing bridges. Enhanced monitoring. Implementing advanced sensor technologies and regular inspections can help identify potential issues before they become critical failures. Public awareness. Educating the public about the importance of bridge infrastructure and the challenges posed by climate change can foster support for necessary investments and policy changes. Cross-sector collaboration. Encouraging cooperation between engineers, climate scientists, policymakers, and industry leaders can lead to more comprehensive and effective solutions. Conclusion. The threat that climate change poses to our bridge infrastructure is a stark reminder of the far-reaching impacts of global warming. As we continue to grapple with rising temperatures, extreme weather events, and changing atmospheric conditions, the safety and reliability of these critical structures hang in the balance. Addressing this challenge requires a commitment to innovation, policy reform, and proactive maintenance. By embracing climate-resilient design principles, investing in infrastructure upgrades, and fostering collaboration across disciplines, we can ensure that our bridges continue to serve as reliable lifelines for generations to come. The stakes are high, but so too is our capacity for adaptation and innovation. As we confront the realities of climate change, let us view the challenges facing our bridge infrastructure not as insurmountable obstacles, but as opportunities to build a more resilient and sustainable future. In doing so, we can once again cross our bridges with confidence, knowing that they are equipped to withstand the tests of our changing world.